J'aimerais remercier tout d'abord les organisateurs de cette école d'été pour m'avoir donné l'opportunité de venir vous faire part des questions qui me préoccupent. And now I'm going to continue the lecture in English. So I want to begin with an overview of the topics that I'll be treating in these 4 lectures. So as a kind of motivation for what I'll be speaking about, so we all know that the Birch and Swinnerton-Dyer conjecture relates the L function of E over Q to various arithmetic invariants attached to the elliptic curve, like the rank of its mod-L-V group, the Shafirevich-Tate group of E over Q, and various, the regulator of E over Q, and so on and so forth. So in a special case, well, not so special for elliptic curves over Q, but in the case where we know that the elliptic curve is modular, so if E over Q is modular, which of course now is known in full generality, then we can attach to this elliptic curve a modular form, f of weight 2 on gamma naught of n. And we can express the L function as a Mellin transform of this modular form, as you heard in the last week's lectures by presumably by Oesterle and Edixhoven. So we can express the L function of E over Q at S as essentially, well, times some factors, 2 pi to the minus S times gamma of S, as the Mellin transform of this form of this modular form of weight 2. So we can write it as integral from I infinity as 0 to infinity of f of I y to the s minus 1 dy. So this suggests introducing the differential omega f equals 2 pi I f of z dz. So this is an invariant differential on h mod gamma naught of n, which is attached to the elliptic curve thanks to the modularity assumption. So this is a differential on h mod gamma naught of n. And the L function at 1 is essentially just the integral from 0 to I infinity of this differential. So we can write now L of E over Q1 as the integral from 0 to I infinity of omega f. So in these terms, the BSD conjecture now implies that, relates the vanishing or not of this number to whether or not the mod-L-V group of E is finite or infinite. So we can express the BSD conjecture in this special case as saying that the integral from 0 to I infinity of omega f is equal to 0, if you want, if and only if the cardinality of E of Q is finite, is infinite or not. Okay, so this, of course, is only a special case of the BSD conjecture, so it's not the full $1 million question. On the other hand, a proof of this would already be, it would already be quite a spectacular advance. And in fact, this statement incorporates one of the 2 crucial difficulties in the Birch and Swinnerton-Dyer conjecture. So I want to look at this statement, and somehow the leitmotif of what I'll be talking about in the next, in this whole lecture series is that, well, this statement somehow expresses the fact that there should be an intimate connection between periods of modular forms and arithmetic of the corresponding elliptic curve. So this is going to be somehow the theme of my lecture series. So a lot of arithmetic information about an elliptic curve E, for most of the lectures, actually, this curve will be over Q, although some of the phenomena that I'll talk about have rather natural generalizations to other settings. So a lot of arithmetic on an elliptic curve can be extracted from the periods of the corresponding modular form. From the periods of the associated form omega f. Now, I want to make this leitmotif, I want to make this more precise and say more precisely what I'll be discussing. To do that, I have to give you some idea of what I mean by periods in this context. So rather than attempting to give a systematic definition, I'm going to illustrate by a number of examples the kind of objects that I have in mind. And of course, and the way in which I use period here in this lecture series is not quite standard. So I'll just illustrate it with a few examples without giving. So the first example, which I'll only touch upon briefly, in fact almost not at all in these lectures, are modular symbols, which so these are obtained by letting alpha be a rational number, which I think of as a point on the extended upper half plane. So if alpha is a rational number, I can consider the integral from alpha to I infinity of omega f. Now, this number belongs to a lattice which is commensurable with the narrow lattice of the elliptic curve, in fact, in a very explicit way, and I'll call this lattice lambda. This is a consequence, so this is commensurable to the lambda E, which is the narrow lattice of E, and I guess this is a consequence of the theorem of Manin-Drinfeld, which I imagine was explained last week in the lectures of Westerle or Erikshoven. So anyway, I mean, so we have this kind of, if you want, integrality properties of these numbers, and these quantities. Well, let me call this lambda E is the narrow lattice. And lambda, I'm being not precise. I'm just saying it's a lattice which is commensurable to. Of course, I could be more precise, but I won't. So this is just this means commensurable. So I'm going to call this number m alpha, and these quantities are connected with special values of L functions of E over Q, twisted by Dirichlet characters. So if I let chi be a character, Dirichlet character of conductor C for C some integer, then I can define m chi to be the sum of chi bar of A times m sub A over C for A ranging from 1 to C. And so this is a complex number is essentially equal to the special value of the L function of E twisted by the character chi bar at S equals 1. So this is a formula of Birch and Manin, which will be mentioned at least in the lectures of Colmes tomorrow. So I refer you for this formula. Sorry, I'm sorry. I wanted to put a chi here.
What's behind it?
Behind it?
Yeah.
This?
No.
So I'm defining m chi to be this.
The sum of chi of I times what?
Chi of A times m A over C. So m of A over C, I mean, okay, one thing maybe one should say is that this m A over C, I mean, m alpha only depends on alpha modulo 1. This follows from the invariance of f of z dz under translation. And so this expression is really well defined. Okay, so therefore, if you stare at this expression, you find the natural conjecture that which relates to vanishing of this period, which is a generalization, of course, of this one. This is just M0. So we're led to expect that the expectation is that M chi equals 0 if and only if the corresponding piece of the Mordell-Weil group is infinite. So I consider the Mordell-Weil group of E over the cyclotomic field generated by the C roots of unity. And this is a finitely generated Z module. Therefore, I mean, the finite group plus a number of copies of Z. I can tensor that with C to make it into a finite dimensional complex vector space in which the Galois group of Q mu C over Q acts in a natural way, and then consider the chi component or the chi bar component, it doesn't matter, of this vector space. And if this is, so the conjecture is that this piece of the Mordell-Weil group is infinite precisely when this generalized, when this period, M chi, vanishes. Okay, so this is, again, I mean, a conjecture which would follow from a fairly natural sort of equivariant generalization of the Birch and Swinnerton-Dyer conjecture, but where the L function doesn't figure explicitly, although, of course, it's very much lurking in the background. Okay, so this, as we'll hear tomorrow in Colmez's lecture, we know something about this statement, namely, thanks to the work of Cato, we have one implication. Namely, yes, this implication holds, and we'll hear tomorrow why, I mean, how that follows. I should mention that the other implication seems to be more difficult, and we don't seem to have at present any tools for tackling the opposite implication, even in the case of if the trivial character were all, as I mentioned before. Okay, so this is one example of, if you want, a reformulation of the Birch and Swinnerton-Dyer conjecture in terms of periods attached to modular forms. Now, this is a setting which has been studied very much. Modular symbols have been used by Mazur and Swinnerton-Dyer to define p-adic L functions attached to elliptic curves over Q. And a lot of connections have been conjectured or eventually proved about this, about the relationship between these objects and the arithmetic of the elliptic curve. Now I'm going, so a second example, which is very much in the back of my mind in this lecture series, which I'll be dealing with in lectures 2 and 3, so another class of periods which are interesting to consider are the so-called Cintani cycles. So in this setting, I'm still with an elliptic curve over the rationals, but I let K be a real quadratic field of the form Q squared with D, so where D is positive. And I make, for now, I'm going to make a number of assumptions about this quadratic field. So I'm going to assume that all the primes L, which divide the conductor N of the elliptic curve, are split in this real quadratic field. I mean, those of you who are familiar with Heegner points and will recognize this condition. We'll see that it's familiar. This is often called the Heegner assumption in the setting where K is imaginary quadratic. And the second assumption I want to make is that the narrow class number of K is equal to 1. This is just for the purposes of illustration. Very, very soon I'll be relaxing that second assumption. So under those assumptions, one can show that there exists a unique embedding C of the ring of integers of K into the algebra M0 of N of 2 by 2 matrices with entries in Z, which are upper triangular modulo N. So OK is just a ring of integers, and M0 of N is this algebra whose group of units of norm 1 is just the group gamma naught of N. Okay, well, what do I mean by unique? Well, so first I have to say, so which is optimal in the sense, no, I don't need to say optimal, but I mean unique up to what? Up to conjugation by gamma naught of n. So of course, if you have such an embedding, you can always conjugate it. So up to replacing phi by alpha phi alpha inverse, where alpha belongs to gamma naught of n. So of course, if you conjugate such an embedding by gamma naught of n, you're still going to get a similar embedding. But up to conjugation, there's a unique one. That actually turns out to be implied by the assumption that the class number, the narrow class number of the real quadratic field is equal to 1. So now let epsilon k be a generator of the group of units of norm 1 in OK star. So generator of the OK1 star, which is the elements of norm 1 in OK. And we can consider gamma k, which is just the image of this fundamental unit of the real quadratic field, or in this case, the square of the fundamental unit, under the embedding C, and this gives us an element, of course, of the matrix algebra M0 of 1, which is of norm 1, in other words, an element of gamma naught of n. And now I'm going to define, so of course, this element is essentially canonical. It's well defined in gamma naught of n up to conjugation. So it gives you, in particular, well-defined conjugacy class in gamma naught of n. So we can now define the period attached to k to be simply the integral from tau to gamma k tau omega f. Okay, so the fact which makes this period a natural object to consider, which accounts for its interest, is that, like the modular symbols, this period is related in a fairly precise way to special values of L functions. So we have the following fact that the square, actually, of this number is equal. So I'm going to be using this symbol a lot. It's an equal sign with a dot on top. It's a very useful piece of notation for my lectures. It means equality up to some non-zero factor, which is a kind of fudge factor, much less important than the terms that appear in the equation that I write down, and which in principle could be written down explicitly. So generally involving powers of pi and so on, but which I won't bother to write down. So the main part of the formula is that the square of this number is equal to the L function of E over K at 1 times some explicit non-zero factor. Okay. And this is the result which is due to a number of mathematicians. It follows from work of Valspurgey, Konen, Zagier, and probably some other people that I'm not mentioning in various contexts. So, well, if we know that, we can make the same kind of conjecture that we did before, that this period jk is non-zero if and only if E of k now is finite. And this, of course, is very much an open question. Now, here, in this case, so this is a conjecture again, but in fact, one can prove this. But in a way which is a little bit, involves a bit of cheating, if we want. The point is that in this context of narrow class number 1, this jk encodes the square root of the special value of L of E over k at 1, but this L function factors as a product of an L function over Q times a twist. And therefore, so this is known. This implication is known, and so that's the sort of the easy or relatively easy implication, is known by using either Kolyvagin, the work of Kolyvagin, or the later work of Kato. But one has to cheat in the sense that one has to exploit the factorization of L of E over K at 1 as a product of two L series, L of E over Q, times the L series of a twist of E, again over Q. Or the L series of E twisted by a Dirichlet character, that's the same thing. Quadratic Dirichlet character attached to K. Well, this is, of course, well, it's not the kind of proof that one would like, for the very simple reason that if I can now relax a little bit the setting and cease to assume that the narrow class number of K is equal to 1. In that case, I have So now let me assume, more generally, that the class number of this real quadratic field is not 1. So in general, we can assume that h plus of k is h, and greater than 1 if you want. And in that case, we can associate to every ideal class in the narrow sense. So if A is a narrow ideal class, we can associate a period J subscript A, which is defined very much like the period J sub K. I'll be more specific in the later lecture when I really delve into these periods. So we can associate a period. So these periods are actually natural bijection to narrow ideal classes in the real quadratic field. So, and we know that there is some relationship between, so we can then define a cycle J chi as the sum over all narrow ideal classes of chi of A times J sub A. And where now chi is a character, it's an ideal class character, which we can think of as a character of the Galois group of the Hilbert class field, or the narrow class field of K with values in C star. And we have in this case a very much the same relationship between J chi and the special value of L of V over K twisted by this character chi. Okay? So this leads to the conjecture that this period J chi is non-zero if and only if the Mordell-Weil group E of H, which I tensor with C to make it again into a finite dimensional vector space, and then take chi component, is, well, finite or trivial. I mean, it's trivial. So that there are no points, if you want, in the corresponding piece of the Mordell-Weil group. So this is a conjecture. And unlike the special case that I wrote here, this case seems to be very much out of reach. Either implication is not within the realm of what we can currently do. So let me just maybe mention the difficulty, because I'll be talking about this in my third lecture, essentially. So what is the difficulty in sort of dealing with this conjecture is that we don't have a conjectural setting for tackling this because, well, we lack the kind of object that Mazur called the algebraic treasure. So lack the needed to define either an Euler system or a Colli-Wagner system in the sense of Mazur, to define an Euler slash or Colli-Wagner system that one would need to approach this kind of question. So, I mean, always the crucial conceptual problem in trying to bound or to relate Mordell-Weil groups to special values of L functions, at least when one tries to adopt the approach that was initiated by Colli-Wagner, is to have a good system of elements, either Heegner points or some kind of algebraic object, which would then allow one to manufacture these cohomology classes which can be related to L values. And so here,
how do you like what do you like?
I said we lack the, well, what Mazur called the algebraic treasure. So if you remember Mazur's block diagram of this morning, there was this notion of, I mean, either Heegner points or some very nice system of points or elements or so that can be then used to on the one hand, manufacture cohomology classes, and on the other hand, can be related to special values of L functions to make the bridge between those two things. So this will be somehow the theme of lecture 3, is to discuss a kind of conjectural setting, or a conjectural setup maybe, for tackling this conjecture. So for maybe beginning to attempt to unearth this treasure, which is still very much buried at present. Okay, so the third example of periods that I have in mind, that I want to really discuss on the same footing, is the example of Heegner points. Which have been already discussed, notably in the lectures of Edixhoven on the work of Cornu. So here, we're going to let K be an imaginary quadratic field. And consider now, given any tau in the complex upper half plane, whose coordinates actually belong to this quadratic imaginary field, I'll define as a period attached to this tau to be simply the integral from I infinity to tau of omega f. Okay, so I'll just associate to tau the period j tau, which is just the integral from I infinity to tau omega f. Now, this period, in some sense, involves a certain choice of base point, namely the base point I infinity that I sort of chose to start with a cusp and integrate up to tau. There's a certain amount of arbitrariness involved in this choice. And really, I could have started with any cusp, and the result would not be so much less, the definition would not be so much less compelling. So it's really natural to think of this number as a complex number which is only defined modulo what I would get by making a change in this base point. And we saw before when we discussed modular symbols that the integral between two cusps of omega f is not some arbitrary complex number, but these integrals generate a lattice, which is essentially almost, the period lattice of the elliptic curve. It's this lattice which I called lambda before. So we can really think of this j tau as being a number in C mod lambda. Okay, now we also have Weierstrass uniformization, which I'll call eta, from C mod lambda. Well, okay, I'm going to do this in two steps. First I want to bring myself to C mod lambda E, the narrow lattice of the elliptic curve, and then take the Weierstrass uniformization attached to, Weierstrass, which is the reverse of the integration of the Néron differential on the elliptic curve. So we have this nice analytic uniformization. Here I would just get this map by multiplying by a suitable integer to bring this lattice into that one. Integer which depends only on E. Now, the sort of arithmetic significance, if you want, of these periods, these j taus, is that, well, we know that the image of these j taus under this analytic uniformization eta are not just arbitrary complex points, but they're actually algebraic points, and in fact their coordinates are defined over certain predictable abelian extensions of the imaginary quadratic field. So eta of j tau belongs to E of h, or let me just say to E of k ab, where k ab is the maximal abelian extension of the imaginary quadratic field K. So this means, already I think the remarkable part of this statement is merely the algebraicity that the image under this very, very highly transcendental operation of integrating omega f to tau and then applying the Weierstrass uniformization, that if you start with an algebraic argument here, more precisely defined over an imaginary quadratic field, you get at the end of this process still an algebraic point, which, as we all know, of course, bears many relationships with the arithmetic of the elliptic curve, and in fact is at the source of many of the breakthroughs that we now have in the direction of the Birch and Swinnerton-Dyer conjecture. So let me just mention regarding this construction that so this gives a plentiful and regular supply of points, of algebraic points in E of I mean, in the more Alveoli groups of E over abelian extensions, or certain abelian extensions of imaginary quadratic fields. And in some sense, this plentiful regular supply of points is not predicted, but certainly justified, if you want, by, or can be justified by looking closely at the Birch and Swinnerton-Dyer conjecture. So this is somehow predicted, with the help of a bit of hindsight perhaps, by the BSD conjecture. And I want to just explain that because it's going to be important for what I'll be discussing later on. So in the following sense. So I'm going to now place myself in a situation which is analogous to the one I had when I was discussing the Shintani cycles over real quadratic fields. I'm going to assume that all the primes dividing n are split in the imaginary quadratic field K, and that that we have a character chi of the absolute Galois group of K into C star, which is so this is a character which is anti-cyclotomic, or maybe I should say rather it's a finite order character. Maybe I should say dihedral type character. So character of dihedral type. Now, what do I mean by that? So I mean that if I take chi of sigma. Now, let me call tau the generator of the Galois group of K over Q. Okay, and now conjugation by tau acts naturally on the Galois group of K ab over K. So I can consider the conjugation of sigma by this involution tau, and I assume that chi of sigma tau is equal to chi of sigma bar or chi of sigma inverse. So that's what I mean by when I say of dihedral type. This is equivalent to the condition that the field cut out by this character is not only Galois over K, but also Galois over Q, but is not abelian over Q. It's a Galois group over Q is a generalized dihedral group. Well, I mean, in fact, it's a dihedral group. Okay, so now, and let me assume that these characters chi are unramified. Let me assume this character chi is unramified at all the primes L, which divide the conductor n of the elliptic curve. Now, these conditions are not really, well, they're important so that what I write now is going to be true, but in the first approximation, you don't have to take them too seriously. Now, the upshot of this is that when we can consider the functional equation satisfied by the L function of E over K twisted by chi at S. Now, this functional equation relates the corresponding L function corresponding to the character chi bar at 2 minus S. That's the usual yoga of functional equations, but because of the specific nature of this character, namely the fact that it's of dihedral type and that the elliptic curve is defined over Q, it's an easy exercise to see that this L function is equal to L of E over K chi at 2 minus S, so that the L function, and more specifically it's the sign of the, so the functional equation relates the L function at S to the same L function at 2 minus S. You can check here that the order factors are actually the same for chi and chi bar. And what's more, these conditions that I've made on the primes dividing n being split in K together with the condition that the character is unramified at all these primes forces the sign in the functional equation to be -1. So that for trivial reasons having to do with parity of in the sign of the functional equation, we find that this L function has to vanish at S equals 1. We get a kind of predictable vanishing for all characters chi of this form. I mean, we're satisfying these assumptions. So, in particular, if I let H over K be any abelian extension of K of dihedral type whose discriminant is prime to n, then for each character of the Galois group of H over K, I get a 0 for all the twists And since the L function of E over H is a product of the L functions of E over K twisted by these various characters, I find that the order of vanishing of L of E over H at S equals 1 is at least, so I find that from these considerations, exploring the factorization of L of E over H, I find that the order of vanishing at S equals 1 is greater than the degree of H over K. So this was an inequality obtained by purely analytic considerations by looking at the functional equation together with the sign and exploiting purely analytic calculations involving L functions. Well, now from the BSD conjecture, we find the following. So BSD now implies that in this situation, the rank of E of H should be at least the degree of the field H over K, which certainly suggests that there's some kind of systematic collection of points which is being produced as you go up, as you vary over all abelian extensions of K satisfying these properties. So this is a sort of conjectural inequality, but which somehow the theory of Heegner points lends some comfort to the feeling that there should be. And in fact, there's a feeling which is, I think was formulated first systematically by Mazur, that Heegner points, in this context that I wrote down here, should account, so Heegner points should account for the bulk. I mean, this is expressed, of course, in a vague way. You have to make that precise. So for the bulk of the growth of E of H as H varies over maybe some natural collection of abelian extensions of K, satisfying these assumptions. And that's exactly, of course, where the result of Cornu that you heard about last week fits in. So this is very much related to the work of Vatsal and Cornu on non-triviality of Heegner points in certain ZP extensions of the quadratic imaginary field. Okay, so a fourth example of periods, which I'm going to want to discuss, are, well, this comes about by considering the following situation. So I'm now going to come back to the case where K is, so 4. This is the setting which I call the setting of Stark-Heegner points. So now I return to the case where K is Q square root D, where D is positive. But I'm going to try to place myself in a situation where this analytic reasoning, which I presented here for imaginary quadratic fields on the order of vanishing of L function, continues to hold, where I continue to have systematic vanishing of L functions twisted by now dihedral type characters for real quadratic fields. And I can do that. I'm going to just present you one setting. I'm going to suppose now that there exists a prime P which divides the conductor of the elliptic curve exactly once and has the further property that P is inert in K. So this immediately places me outside of the scope of the setting of Shintani cycles attached to gamma naught of M, which I discussed in my example 2. And I'm going to suppose otherwise that all the other primes, which divide N over P, are split in this real quadratic field. Now, an identical, for the L function of E over K, now where K is a real quadratic field, one can prove the analytic continuation of its L series in exactly the same way as for imaginary quadratic fields using Rankin's method. And so we still have, I can actually leave this unchanged. We still have a functional equation. Under these assumptions, the sign of the functional equation is still -1. So that means that we have now the systematic vanishing for all twists, and therefore we know that the order of vanishing of L of E over H is greater than the degree of H over K for any extension H of this real quadratic field, which is of dihedral type. So we are led to expect, again, from the Birch and Swinnerton-Dyer conjecture, that the Mordell-Weil group of the elliptic curve over these kind of extensions should grow in a predictable, systematic way. At least that the rank should go up by the degree of H over K. Now, the real mystery is, where do these points come from? So that's, of course, now we're outside the scope of Heegner points, since we're working over abelian extensions of real quadratic fields and not of imaginary quadratic fields. So this is one of the mysteries of the subject, which might appear to be less daunting than the Birch and Swinnerton-Dyer conjecture, because it's still related to situations where the order of vanishing is equal to 1. But the sort of very basic question is, where do these points come from when K is a real quadratic field? So I'm going to, so in lecture 3, what we'll do, as part of the process of understanding the connection between the Shintani cycles and the arithmetic of elliptic curves, we're going to introduce certain p-adic periods. Now, these periods are going to be defined by, still analytically, by a limiting process, but which is going to involve p-adic integration and not usual complex integration. So we'll define p-adic periods, which I'll call j tau, in Cp star mod q to the z, with the property that the image of this periods, j tau, under the Tate uniformization, which a priori belonged to E of K, actually, I mean E of Cp or some, some p-adic field, actually belonged to E of H. Of course, I put a question mark here because I'm very far from being able to prove this property of these periods, which we're going to define. But we can at least write them down explicitly and check numerically that this is the case. So what the constructions that I am going to explain in lecture 3 suggest is that the philosophy coming out of the theory of complex multiplication, that it's possible to construct points on abelian extensions or on elliptic curves using the theory of complex multiplication, actually should go beyond the theory of complex multiplication. There should be there should be situations where we can write down periods and use those periods to construct algebraic points on elliptic curves in situations which are not within the scope of the classical theory of complex multiplication. Okay, so I'm going to now just briefly mention a fifth example of what I have in mind about periods, which are related to the Mazur-Tate circle pairing, and which will be the content of my 4th lecture. So here again, I let K be a real quadratic field. To simplify the exposition, I'm going to assume here that the class number of K, the narrow class number, is equal to 1. Now, Mazur and Tate defined a canonical, what they call circle pairing, which I'll call, well, shall denote by this, and of course I'll explain in lecture 4 how exactly this pairing is defined. So it's defined on the set of rational points on the elliptic curve cross the Mordell-Weil group E of K minus, where this E of K minus denotes the group of points on E of K on which the involution in gal K over Q acts as minus 1. So you can decompose the Mordell-Weil group into a plus part and a minus part under the action of gal K over Q. And there's a certain pairing which takes values in R modulo the logarithm of the fundamental unit of norm 1 of the real quadratic field K. So it's called the circle pairing because this, well, it takes values in a circle group, which presents notable difficulties if you want to use this pairing to define a regulator. And so it's a kind of mysterious to actually formulate a general Birch and Swinnerton-Dyer conjecture which would somehow account for this circle pairing. So it was a conjecture, I mean, it was a question raised in this paper of Mazur and Tate, what would be the meaning of this circle pairing. And for me, I would be satisfied if I could make some kind of, find some kind of connection between this circle pairing and values of L functions, for example. Now, it turns out that one can sort of get a fragment, and this is what I'll be presenting in lecture 4. So a conjectural fragment of a BSD type conjecture in which the usual Néron-Tate height is replaced by the circle pairing. So where the circle pairing of Mazur-Tate replaces the Néron-Tate pairing that appears in the classical conjecture in defining the regulator. And then, well, what replaces the L function of E over Q? That's, of course, the difficulty in this thing, because we don't have a sort of... And it turns out that the correct object which replaces the L function of E over Q is, in order to sort of guess at this object, one has to think really of the L function in terms of the period. So what we can kind of define is an object which we call a derived period. In fact, I'll write it down. I don't want to make any mystery about what this period looks like. It's just the integral from tau to gamma tau of omega f times the logarithm of z minus x gamma over z minus y gamma, where x gamma, y gamma in P1 of R are the fixed points. Of gamma. Sorry, I should say this is gamma k. The same gamma k that I defined in my earlier example when I talked about Shintani cycles. So you just integrate omega f, but against this rather simple expression, the logarithm of this rational function which has 0 in poles x gamma and y. X gamma at the fixed points of gamma k. So actually, one exercise that you can this of course you see depends on a choice of base points, tau. And the first computation to do to check that this would eventually make sense is to see that this does not really depend on the choice of base points, or not too badly. It only depends modulo a lattice which is generated by the dilation of the lattice lambda that I had before by the logarithm of the fundamental unit of the real quadratic field. So we view this in C modulo lambda times the logarithm of epsilon k, well, provided, and this is a crucial thing, that tau is not just an arbitrary base point, but we have to require that it actually be a cusp. Okay, so I'll talk about this more in lecture 4. Okay, so now, in the last 10 minutes that I have, I'm going to begin by going into the beef of the lecture. And what I want to begin by doing is to place this discussion of periods, which has been until now largely an Archimedean discussion. So what I presented here are various examples of periods in the Archimedean setting. It's useful to paint a parallel picture in which complex analysis is replaced by p-adic analysis. Okay, so this is sort of the first topic of my lecture series. I'm going to talk about p-adic integration and a p-adic analog of the theories that you heard about, the notion of modular parametrization and so on, that you heard about last week in the first lectures of Edixhoven. So I'm going to talk about, so I remind you that in the complex picture, when we have a modular elliptic curve, we can write E of C as a quotient of the curve h modulo gamma naught of n, this map being given explicitly by sending an element tau to the integral from I infinity to tau omega f. Eventually, this is a complex number, so I apply to that the Weierstrass uniformization eta. So you heard about this, of course, in Edixhoven's lectures. And all the periods, most of the periods that I alluded to in my introduction, involved integration of this complex differential omega f. Now, what I'm going to explain now is that it's possible, so this is going to be my goal in the remaining 10 minutes of today, and I'll continue, of course, with that in the next lecture, to replace the complex numbers by the p-adic by Cp. Well, so where Cp is a sort of p-adic analog of the complex numbers, it's just the completion with respect to the p-adic distance of the algebraic closure of the completion of Q with respect to the p-adic. So it's the algebraic closure of Qp. So if you take the algebraic closure of this complete field, you get something which is not complete, and you have to take a further completion, and what you have is still algebraically closed. It's a rather large field which, for many purposes, can be used to replace the role of the complex numbers in our analysis. Now, we're going to, well, what is going to play the role in this picture of the complex upper half plane H is going to be a p-adic analog, which is obtained very much in the same way as H by taking the complement in P1CP of P1QP. So I'm going to let HP be, by definition, the complement of P1CP, of P1QP and P1CP. Now, this is analogous, you'll observe, to letting H be the complement of P1 of R in P1 of C, except that, of course, that is not the usual way that we define the upper half plane. This is a union of two of the complex and lower upper half planes. But in the p-adic context, when we remove a P1QP from P1CP, we don't break up the P1CP into two disjoint halves in any natural way, so it's just better to work with the whole object. So this is what plays the role of H. So what I want to do is to, so we're going to see, that's going to be the program of tomorrow's lecture. So we're going to see that we're going to try to attach to E a rigid analytic, and I'll define I'll develop from scratch enough of the basic notions of p-adic analysis to make precise what I'm going to say next time. So a rigid analytic differential form, which I'll again call omega f, even though it's completely different from the omega f that I had in my introduction, which is going to be on HP modulo gamma, where gamma is a certain discrete subgroup of SL2QP, which, well, so gamma is contained now in SL2QP. So this, is the program, if you want. And we're going to now use, and then after this, we're going to use omega f to define p-adic periods, which should bear the same kind of relationships to complex periods, as complex periods to special values of L series. And to kind of situate what I'm going to be saying next time, I'll make a little chart. So we had, now let's see. So, in some sense, when we looked at H modulo gamma naught of n, we had three kinds, at least in my introduction, I mentioned, roughly speaking, three kinds of purely Archimedean periods attached to the differential attached to E. So one were the modular symbols. The second class were the Shintani cycles attached to real quadratic fields. And the third class of examples were the Heegner points, or the line integrals whose image give rise to Heegner points. Now, in the p-adic setting, we're going to develop in the next lecture analogous p-adic analytic uniformization of the set of CP points on the elliptic curve by some quotient of HP by some other arithmetic subgroup of SL2QP. And we'll see that for the form which corresponds to this uniformization, there are similar kinds of periods that you can define. Well, the modular symbols don't seem to have any analog in this setting, essentially because discrete subgroups of SL2QP do not have parabolic elements. That's going to be one difference. However, the Shintani cycles and the Heegner points do generalize nicely and give rise to p-adic Shintani cycles and p-adic Heegner points. Okay, well, you might ask, what is the motivation for launching into this sort of p-adic digression? And I'll just, to conclude my lecture, today I'm going to just mention two motivations for developing the theory, which I'm going to explain next time. So, the motivations. The first motivation that I have is that, as we'll see when we talk about p-adic Shintani cycles, we're going to attach to certain imaginary quadratic fields a cycle, jk, which is defined in a very analogous way to the Shintani cycle attached to real quadratic fields. Now, on the other hand, in the p-adic setting, there seem to be some certain phenomena which are somewhat more rich than in the classical Archimedean setting. And the main thing is that these Shintani cycles, so p-adic Shintani cycles, maybe I could say deform naturally to certain p-adic families of periods, J, C, S, where S is a p-adic variable, is in ZP. So it's possible to just stare at the definition of the p-adic Shintani cycle and view it as a specialization at S equals 1 of a family indexed by a p-adic variable S. So because this variable is a continuous p-adic variable, of course, this can be used to define p-adic L functions. So of a kind which are quite different from the p-adic L functions which we'll hear about tomorrow in Colmez's lecture, the sort of classical p-adic L functions of Mazur and Swinnerton-Dyer. These are essentially L functions which are attached to different abelian extensions of a quadratic imaginary field, in the anti-cyclotomic ZP extensions. So we can get sort of, I don't know what to say, sort of maybe somewhat slightly less standard p-adic L functions in a fairly natural way by looking at these families. And for these p-adic L functions, we have enough machinery to prove certain main conjectures. So for example, we can show that the order of vanishing at S equals 1 of these JCS is at least the rank of E of K. So, or maybe, well, let me put E of Q here to be safe. So we can relate somehow the order of vanishing of these families. Once we have a family which varies according to a continuous variable, you can of course look at its higher derivatives, and these kind of statements become much more tractable than the corresponding complex Birch and Swinnerton-Dyer conjecture, because the p-adic L functions are closer to cohomology than are their complex counterparts. Well, that's one motivation for going into the p-adic setting. The second is that p-adic integration is a crucial ingredient, at least on a motivational level, for defining the Stark-Heegner points attached to real quadratic fields. So Stark-Heegner points attached to real quadratic K over Q seem to require p-adic integration, as far as I can tell at this point. So that's the plan. The plan of the next lecture is to develop enough of the machinery of p-adic integration that I can define all these p-adic analogs of classical periods attached to modular forms. And then in the last two lectures, lecture 3 and 4, I'll talk about p-adic Stark-Heegner points and the derived periods and their connection with the Mazur-Tate circle pairing. Thank you.